If you'd like to learn about digital to analog converters, including how to interface them to a microcontroller, then stick around. Welcome to the electronicshobbyblog.com. I'm your host, Dominick Soldano, and today we're talking digital to analog converters. That's right, DACs. We'll look at what they are, important parameters you need to consider when selecting a DAC, how to connect them to a microcontroller, and how to access them via the microcontroller's I2C interface. In particular, we'll look at the MCP 7425, a 12-bit I2C interface DAC with built-in EEPROM for persistence. Let's get started. A DAC takes a digital signal and converts it to an analog voltage. DACs are used in many different products. Every CD player or digital audio player has a built-in DAC. The DAC takes a stream of digital data coming off of the laser record head and converts it to an analog signal or waveform that becomes the audio that we hear played through the speakers. A lot of modern test equipment uses a DAC as well. For example, in a digital power supply, the microcontroller sends out a digital setting, which is then converted to an analog voltage that drives the regulator. In digital signal processing, we take a stream of digital data and convert it to a waveform. DACs come in a wide variety of packages. The one we'll be using today comes in a very tiny SOT23 package, but you can also get them as dual inline packages, QFN flat packs, or a variety of other package styles. At the heart of most DACs is a resistor network that converts a byte of data into an analog voltage. The resistor network is set up in such a way that each bit in the word contributes a proportion of the voltage equal to its position in the word. For example, the most significant bit contributes the largest. The bit just below that contributes half of what the most significant bit contributes. And so on and so forth as we move down the line. The resolution of the DAC is controlled by the number of bits. This example shows what would be the resistor network for a 4-bit DAC. We can also look at an example for an 8-bit DAC. The most significant bit contributes twice as much to the output voltage as the bit just below it. This is a traditional layout for a DAC resistor divider network. Notice the use of R and 2R. You don't need an integrated circuit DAC. You can build yourself a DAC using this resistor network. And here's another topology used for the resistor network. In this case, as we move from most significant bit to least significant bit, the value of the resistor doubles, ensuring that each successive bit contributes half as much to the output as the previous bit. This particular topology is also available in an 8-bit version. You can keep expanding this to as many bits as you need. In fact, some DACs support up to 32 bits. A resistor network by itself isn't very good. What we really need is some way to buffer the output of the DAC. And to do that, there'll often be a buffer or amplifier on the output. Here's an example for the first resistor network topology we looked at. In this case, the feedback resistor can be used to control the gain of the amplifier. So it's possible to have a microcontroller running at 3.3 volts, but have the analog signal out be much higher or lower than the voltage that the microcontroller runs at. And here's how we'd hook up that amplifier in that second resistor network topology. One of the key factors we have to consider in selecting a DAC is the DAC's resolution. And the DAC's resolution is controlled by the number of bits. For an 8-bit DAC, for example, we would have 256 unique states. So the resolution of the DAC is 1 part in 256. For a 10-bit DAC, it would be 1024 bits. And so the resolution of the DAC would be 1 part in 1024. Another important parameter to consider when selecting a DAC is the step size. And step size is very closely related to resolution. Here's a table that compares resolution and step size for different voltage values. Let's take our MCP 7425 for example. It's a 12-bit DAC, which means it has a 4096 resolution. If we use 5 volts as the reference voltage, then we can expect each step to be equal to 5 divided by 4095. Right? So from 0 to 4096 is 4095 steps. And that comes out to 1.22 millivolts per step. So that's fairly fine control. But we can actually get much finer control if we went with a 16-bit DAC. we'd be able to get down at 5 volts input to 76 microvolts per step. And here's the block diagram of a single channel I2C interfaced DAC. Notice in the block diagram that it calls out a resistor network. And that's the very resistor network that we talked about earlier in this lesson. There's a whole bunch of other control circuitry that's in there as well. There's a number of registers. Some DACs have an external reference voltage. This one shows an external reference voltage, and so you can switch between internal and external reference voltage. The DAC we're going to look at today is fairly simple. It's a single channel DAC also, but it uses VDD, or the supply voltage, as the reference. So there's no separate external reference. If you need real precision, you want to select a DAC with an external reference. And here's another DAC example. This DAC includes 4 channels, or 4 separate DACs in one package. And each one can be independently controlled, and each one can have its own reference voltage. And the reference voltage is what determines the maximum value that the output of the DAC can reach. It's also important to note that the output of the DAC's accuracy is only as good as the accuracy of the reference. So if you need precision, you probably want to use a precision voltage reference as the reference input to the DAC. Here you see a lot of the parameters that you need to choose between when you select a DAC for your project. Let's take a look at some of the more important ones. Key DAC considerations are going to be the number of channels. How many specific DACs do you need? If we were building a dual output power supply that allowed us to control both the voltage and the current limit, we would need 4 DACs. 1 for voltage, 1 for current control, and then we'd need that for both channels. So we could use a quad channel or 4-channel DAC and get all 4 DACs in a single package. The number of bits of resolution is also a key consideration. How precise do you need to be able to control the output? What is the minimum step size that you need to control? All of those things will be determined by the number of bits. And you can get DACs from just a few bits all the way up to 32 bits. As I mentioned earlier, the DAC we're working with today is a single channel 12-bit DAC. Another key parameter in selecting a DAC is whether or not you need an internal or external reference source. DACs with external references can be much more precise. The DAC's precision is limited by the precision of the voltage source. So if you need really precise output, then you want to make sure that you select a precision voltage reference and use that as the reference input for your DAC. In addition to considering what we want the DAC to use for its own power rail, we also need to consider what the maximum analog output voltage we want. Some DACs will have built-in programmable gain amplifiers. That would allow you to use a 3.3 volt microcontroller, but get a voltage output swing on your DAC of, let's say, 0 to 12 volts. So let's take a look at our MCP 7425. Here are some sections I extracted from the datasheet. This particular DAC has a 12-bit resolution. It's got an EEPROM built in, and the start voltage when we first turn it on will be determined by what we've programmed into that EEPROM. It's got an external address pin, which means that we can use 2 of these DACs in the same circuit and through hardware set them to have independent addresses. It has a wide operating voltage range, so we can use it with 3.3 volt microcontrollers or with 5 volt microcontrollers. The MCP 4725 comes in a 6-pin SOT23 package. Let's look at each of the pins and what they control. VDD is the supply voltage, and this particular DAC uses the supply voltage as the reference source. And so your output voltage is only going to be as stable or only as precise as your VDD or supply voltage. VSS is ground. A0 is the address bit, and we can tie that either high or low depending on what we want the address of this DAC to be. Vout is the output, and SCL and SDA are the I2C interface pins that we'll use to send data to the DAC. Here's some more key information from the datasheet. Let's take a look. Notice that the MCP 4725 draws very little current. That means that if we want to, we can power it from a precision voltage reference. When we connect this, we'll need to use pull-up resistors on the SDA and SCL lines. So here's how we're going to connect this to the microcontroller. I'll be using a particle photon today, but the way you connect it to an Arduino is almost exactly the same. You just make sure you're using the SDA and SCL pins on the Arduino. The particle photon runs at 3.3 volts, but it has a 5 volt input line. In addition, all of the digital pins on the photon are 5 volts tolerant. So I'm going to take advantage of running this off a single 5 volt regulated supply. We'll connect VDD to our 5 volt source and also connect 2 pull-up resistors of 10K each to the SCL and SDA lines. VSS, or pin 2, is our ground. Vout is on pin 1. We're going to set this to have the A0 bit grounded, which will set that particular address line to 0. Pins 4 and 5, the SDA and SCL lines, will connect up to the photon's SDA and SCL lines. Before we can build the circuit, we're going to have to take that tiny SOT23 chip and solder it to a breakout board so that we can use it on a solderless breadboard. Here I'm test fitting the chip on a breakout board that I bought from Adafruit. I've got a bunch of these for different types of chips. I found the best way to solder these in place is to use a little bit of solder paste. It doesn't take much, just the tiniest amount on the contacts. You want to be careful not to get it everywhere, but if it bridges the contacts, that's okay, because capillary action will cause it to wick back under the pins once we heat it up. Placing the chip on the solder paste will hold it in place so that we can solder it. You want to get it lined up correctly on the pins so that there's no bridging that takes place between the pins and the pads. And once you've got it set, you just hold it in place and apply a little bit of heat to the pins. The solder will melt and it'll wick away from the areas between the pads and settle under the pins. You want to be careful not to apply too much heat and damage the chip. Once I had it soldered in place, I went ahead and ohmed it out to make sure that there were no shorts and that all the pins were connected. And here's a useful trick for soldering headers to a breakout board. If you insert them in a solderless breadboard, then the solderless breadboard will hold them at the right angle, straight up and down, and maintain the proper spacing between them. Once you do that, you can put the breakout board on top and solder it in place, knowing that everything will come out nice and square and evenly spaced. And here's the circuit all hooked up. It exactly follows our schematic. The one thing to keep in mind, you need to be careful when you connect the DAC to make sure you remember which is the number 1 pin. I always install my chips on breakout boards so that I can read the text right side up, and then the 1 pin is at the top left. That means that whenever I pull a pre-soldered breakout board out, I know exactly where the 1 pin is. So let's look at how we control the DAC, or how we interface the DAC via the I2C interface. We need to send 4 bytes to the DAC. The first byte that we send is the device address, and it's 7 bits long. The address consists of a device code, which is fixed at 1100, and then 2 address bits that are set at the factory. The DAC that we've purchased is preset for A1 and A2, both equal to 0. The A0 bit is what we can set ourselves using the A0 pin on the DAC, and we've set ours to 0. 11000000 comes out to 60 in hexadecimal. We'll send that byte first over the I2C bus to wake up the chip and let it know to start listening. After that, we'll send a command byte instructing the chip what we want it to do. The chip supports 2 separate commands. Write DAC, which writes the next 2 bytes to the DAC itself, or write DAC and EEPROM, which writes the next 2 bytes to both the DAC and the EEPROM. The EEPROM is read at startup, and that's what's used for the initial output voltage on the DAC. So we can use that EEPROM to tell it what voltage we want it to have at startup. I did some experimenting, and by default, it's set to the middle of the range. So when we first power up the DAC, the output is halfway to VDD. There are only 2 command bytes. As we mentioned, write DAC, which is a command byte of 40 hex, or write DAC and EEPROM, which is a command byte of 60 hex. After the command byte, we can actually send the 12 bits of data that the DAC will use in its register. Those 12 bits are actually contained in two 8-bit bytes. The first byte contains the most significant bit down to D4. It's the left 8 bits of the 12-bit value. The second byte contains the least significant bit and the 3 bits moving up from that. So that is the last 4 bits of the 12-bit value. And then the right 4 bits in that second 8-bit value are ignored by the DAC. Let's take a look at how we implement this in code. We'll actually write a small library for the MCP 4725. So first, credit where credit is due. When I first started experimenting with the MCP 4725, I went out searching to see if there was existing code to control it. And I did find a library from Adafruit. Now, I started with that library, but I've modified it pretty extensively and simplified it. In the Adafruit library, both commands were handled by one subroutine, and you simply set a flag. But I didn't see any reason to run through that code each time you just wanted to set the register value. Depending on your application, you're probably only going to set the EEPROM value once. I made a number of other changes to simplify it and cut it down to its bare bones form. I would like to thank the folks at Adafruit for the start they gave me on this code. So let's start by declaring a class for the DAC, along with its member variables and methods. We need to include the wire library, which is in wire.h. Next, we use two define statements to assign the commands their binary values. Command write DAC gets assigned 40 hex, and command write DAC and EEPROM gets assigned 60 hex. Then we define a class for the MCP 4725 that includes public methods for a constructor, a begin method, which will start the wire library running, a set voltage method, which will set the DAC's register, and a set EEPROM method, which will set both the DAC register and the EEPROM. In addition, we create a single private member variable, which is the I2C address of the DAC. And if you remember from the bit field, that was 60 hex. Now that we've defined the members and variables for the class, let's go ahead and write the actual code. So here's the CPP file. We include the wire.h library because that gives us all of the I2C functionality we need, followed by the h file, which defined our class. We create an empty constructor, and then the first method that we create is the begin method. And the begin method sets the address to the I2C address of the chip and then calls wire.begin. Wire.begin starts the I2C communication process. Next, we implement the set voltage method. The set voltage method takes a single 16-bit unsigned integer, which is the value that we want the DAC to have. We call wire.beginTransmission with the address of the DAC chip. That wakes the chip up and puts it into listen mode for the next 3 bytes. The second byte that we send is the command byte, and that will either be write DAC or write DAC and EEPROM. In this case, since we only want to write to the DAC's register, we're using command write DAC. Then we need to send out 2 separate bytes containing the left 8 bits of the 12-bit value and the right 4 bits of the 12-bit value. We take our output value and we divide it by 16. In binary math, dividing by 16 will lop off the rightmost 4 bits, leaving us with only the leftmost 8 bits, which is what the first word that we need to send must contain. The second command, we do a modulo 16, which means we're dividing and then taking just the remainder. In this case, that leaves us with just the right foremost bits of the 12-bit word, which we then logically shift left by 4 bits. That takes those rightmost 4 bits and puts them in the leftmost 4 bits of the 8-bit word. Once we've sent both of those values to the DAC, we send wire.endTransmission to tell it we're done. The last and final method that we're implementing is the set EEPROM method, and this sets both the DAC register and the EEPROM. The only difference between this method and the one above is the command. All in all, it's a fairly simple bit of code. It really doesn't take much to control this particular DAC. Now let's look at an example of using the DAC in a sketch. Here's the code. So again, we start by including the wire library and the .h file for our DAC class. The first thing we do is to instantiate an instance of the DAC class. Within our setup section, we call DAC.begin and pass in the address of the DAC. In the loop section, we set up a 32-bit integer counter, and then we've got two for statements that simply continue to increment the counter till it reaches 4095 and output the value to the DAC after each increment. And then once it's gotten from 0 to 4095, it counts backward from 4095 to 0 and outputs that value to the DAC. And here's a picture of what we end up with at the DAC output on the oscilloscope. Notice the period of our triangle wave is approximately 3 seconds, and that's running full out. This particular example also shows the limitations of using an I2C interface. Let's look at how many different operations and clock cycles it takes to put that out. First off, we run through about 8,200 writes, and for each of those writes, we've got to write out 4 8-bit words. So that's 32 bits that have to be written out, and then there's overhead, right? So there's probably some information that goes out before and some information that goes afterward for handshaking. So let's assume 50 bits. So we'll assume that we're writing 50 bits each time, and we're doing that 8,200 times. So that's about 400,000 cycles. Well, guess what? The I2C bus, in this case, is running at 400 kilohertz. So when you consider settling time and other times, you can see why it would take 3 seconds. You wouldn't want to use the I2C interface if you're doing anything that requires generating a precision waveform quickly. However, if you're using the DAC to control a power supply output, or something where it only needs to send out a couple of hundred writes every few minutes, it's not a problem at all, and the I2C interface is a pretty good way to go. So just as an experiment, I tried using one of the internal DACs on the particle photon. And here's the code and output. Basically, we generated the same triangle wave. In this case, the period is about 35 milliseconds. That's about 100 times faster than using the I2C bus to control a DAC. That's just a little insight. You know, if you've got to do things fast with the DAC, you either want a parallel DAC or you want a chip that specifically has a DAC built in and uses a parallel interface. To do the accuracy test, I set up a simple circuit with a push button, and every time I pressed the push button, I would increase the DAC value by 1/10 of its total resolution. Starting at 0, the first time I pushed it, the output value would be 1/10 of the total value of 4095, so 409. Second time I pushed it, it would output 819 or 2/10 and 3/10 and so on until I got through 10 pushes, in which case it would output the full value of 4095. Let's see what I found. So here are the results of that test. The predicted voltage is based on the supply voltage, which I measured at 5.049 volts, divided by 4095, and then multiplied by the DAC register value. The measured voltage is what I actually saw on my meter. And you can see that there's quite a bit of difference between the predicted value and measured value over the range of the DAC. In some points it's fairly small, and at other points it's fairly large. For example, at 3/10 of the total output value of the DAC, we have less than 1 least significant bit of difference. But at the top of the range, we have more than 40 least significant bits of difference. I ran the test a second time, but this time I actually output 4095 and measured the maximum output value of the DAC. The measured voltage on pin 1 was 4.999 volts. I redid the predicted values using that maximum output voltage and then compared the measured values against the delta. In this case, the DAC was much closer. So if you want a more precise value, make sure to measure the maximum output voltage of the DAC using your exact power supply, and then do all of your math based on that maximum number. And now you have all the information you need to start incorporating DACs in your own designs. Well, I hope you enjoyed that and that you learned a little something. If you did, then how about a like and a share, and smash that subscribe button. And until next time, cheers.